right, now that we know what an atomic orbital is, let's talk some more about them. In this presentation, we'll apply the idea of probability function to pictures of atomic orbitals. We'll look at the shapes of the s, p, d, and f atomic orbitals, as well as their orientation in space. While we look at the orientation of orbitals in space, we'll explain how many degenerate electrons can be in each shape of atomic orbital, and finally, we will briefly introduce quantum numbers and orbital filling rules. So as you recall, h psi equals e psi is a probability function. We have a 3D representation of that. Atomic orbitals are probability functions in 3 dimensions. We're going to pick up where we left off from the previous presentation. So the 3D representation here gives a diffuse cloud that shows the probability is less in areas with less color and more in areas with more color. If you look carefully, this includes some additional information. First, you notice that there are 2 colors. Why is that? We want to distinguish between different bands of electron density. It turns out when you have more than one electron, the probability function changes a little bit. With one electron, you get the s/1 representation, this one right here, where it's just a sphere, and there is a node at the center of that sphere that you can't see, but a node is a place where there is 0 electron density. So why do you have that node? Well, it turns out if you put an electron in the nucleus, it would combine with a proton, and then it would become, together, those 2 things, a neutron, which means the electron is gone. So we cannot have an electron overlapping the nucleus. It is a tiny, tiny orbital, this S1, and it has very low energy. And recall that the smaller the radius, the lower the energy of the electron. So Bohr's model gave us a radius, but as you can see from these, the radii are a bit trickier of a concept when we're talking about probability functions. We generally go with the 90% confidence interval, call it a day. Like, that's about this wide across. Now, as you go down, we have 1, 2, 3, 4 here on the side. Each level you go down, you get a jump in size. So every time we go up, this 1, 2, 3, 4, you get a jump in size. 1, 2, 3, 4 on the right are principal quantum numbers. They describe the relative size and thus energy of the electrons in these orbitals. The electrons contained in the orbitals with the principal quantum number are said to be in that shell. It's an electron shell. So we have the first electron shell, the second electron shell, the third. You get the idea. We will get into how many electrons are contained within each cell in another slide. All right, so let's correlate this back to energy level diagrams. You remember the electron or the energy level diagram for hydrogen. This is slightly different than the other representation I gave you, but it still has the same idea. But on this one, it's to scale. You can see that the energies are labeled on the left-hand side. The relative jump in energy is highest from the principal quantum number to the second principal quantum number. So the first to the second, n equals 1, n equals 2. Principal quantum number is designated by n. Okay, so we get a big jump when we go from 1 to 2. But if we go from 2 to 3, it's a much smaller jump. 3 to 4, smaller than that. 4 to 5, smaller than that. This is a very uneven ladder. If you were to try to go up this in the dark, you would be SOL. So each step becomes a smaller step in energy. That is why there are gaps in the spectra we've looked at, the line spectra. You notice how like sometimes it's a really big space and sometimes it's really tiny. This is why. This is why you see that. Sorry. So anyway, the smallest energy on the diagram is n equals 1. Note that the value is in fact negative. So negative 13.6 is in fact much less than negative 3.4. The nice thing about this particular diagram is that it is to scale, so it makes everything easier to see. So let's get back to the idea of the atomic orbital shapes. Okay, so I have enlarged just the bottom row, and we're going to talk a little bit more about these nodes that I mentioned previously. So when you add more and more layers of electrons, right? When you have one electron, it's just going wherever it wants. Once you add a second layer, it will have a node where the first electron is most likely to be found. You can see this, though it's not incredibly great, in the fourth layer. So we're at the fourth layer. If you go to the spheres here, we go blue, yellow, yellow. And this is talking about different layers of the same thing. And each time you have that change in color, you have a node at the very center where you don't have electron density. That node corresponds to the layer before it. So you can't have two things in the same place at the same time kind of deal, but it's a little bit obscured because you're talking about probability density. Yeah, not confusing at all. Anyway, so you have these nodes each time you go out further and further, and you can see that they're happening on each type of orbital, although it's kind of obscured in the f orbital. Okay. Now, in addition to having these spherical nodes, we also have nodes that are on planes, and I'm going to try to draw one. So we look at the p-axis. We get a node here, and we get a node coming through here. So these are nodal planes. And this is not very well drawn, but I hope you get the idea. So instead of just a point or a sphere where we don't have electron density, we have an actual plane where you don't have electron density. There are 2 of these planes on the p orbital, there are 3 on the d orbital, and there are 4 on the f orbital. Okay, I'm not going to bother trying to do this for d and f because it's already kind of sketchy on p, and we're at the limit of my artistic ability. But know that the number of nodal planes is equal to the secondary quantum number, which is L. S corresponds to 1, P corresponds to 2, D corresponds to 3, and F corresponds to 4. Okay, so hopefully that'll be easy to remember. Nodal planes equals the angular momentum quantum number L. And we'll get more about how those values are used later. But there we go, nodes. Okay, each orbital can hold 2 electrons. You have, in the s orbitals, we have one thing going on here. We can have 2 electrons in that orbital. We have 3 in the p, right? We have x along the y and along the z for a total of 6 electrons. We have 5 possible d orbitals for a total of 10, and we have 7 possible f orbitals for a total of 14. Now, we already talked about the principal quantum number corresponding to size, but these shapes, this SPDF, correspond to a subshell or angular momentum quantum number, and we already mentioned that. That was your L. Okay? L equals 0, 1, 2, and 3 for S, P, D, and F. I like to think of it as the shape quantum number. Chemists traditionally call the spherical orbital the S. The 2 ovoids next to each other we call the P. And if we're looking at them on the end, they sort of look like this, with like a little break in the middle, barely noticeable. It's vaguely like a figure 8. If we do the same thing, but for the d orbital, it sort of looks like 2 figure 8s, maybe a butterfly if you're so inclined, possibly an X depending on what your style is. But either way, that's if you just look down on the end. So these are ways to remember the shapes of these things. And finally, f orbitals are messy, and I'm not very good at describing them, so we're just going to leave it at that. You can look at the pretty colors. I will not require you to know the shapes of the f orbitals. If you take inorganic chemistry, you'll have to memorize them then. We're not doing that. The orientation of the orbital in space is governed by the magnetic quantum number, which is designated by m sub L. Okay, so L gives you shape, m sub L gives you orientation in space. So that's whether you're along the x, the y, the z axis, or if you're along a plane like the d, the xy, the xz, etc. So because you can orient along the x, the y, and the z, you have 3 different p orbitals, and they are all the same energy. They are degenerate. Degenerate meaning same energy. You can fit a total of 6 electrons in them because 2 electrons for every orbital. And at this point, we have come full circle on this topic. So let's get into the rules of how these things fill, how the electron orbitals fill next. So there's several rules we follow when we fill atomic orbitals. The off-bow principle says that we need to fill lower energies first. So we go from lower to higher energy. But which energy is the lowest is not as clear as going through the principal quantum numbers, which you kind of hoped it would. Instead, as you go up in energy, because the levels get closer together, some of the higher energy subshells in one shell on the bottom overlap with the next shell up. You can rank them using this trick. And I'll show you another trick later in a different presentation, but this is one that lots of people use. So if you write out all the allowed orbitals for each quantum number evenly spaced in successive lines, so we've got 1s on the top, 2s, and then space 2p, 3s space 3p space 3d, 4s space 4p space 4d space 4f, you get the idea. And you can keep going with this. And then we draw diagonal lines through them. We can get the ranking for the order. So 1s is lower energy than 2s, which is lower energy than 2p, which is lower energy than 3s, which is lower energy than 3p, which is lower energy than 4s, which is lower energy than 3d. Wait, what? Up until now, we've been going up in principal quantum number, but we just went from 4s to 3d. And then we're going to go to 4p, and then to 5s. And then to 4d, and then to 5p, and then to 6s. You get the idea. And you can see where it starts to get out of order is when we go from the 3s to the 4s. Because at that point, they're so close together, we get weird jumps. Okay, our second is Hund's rule, which says that you can fill degenerate orbitals each with 1 electron before doubling up. So you fill the p sub x, and then the p sub y, and then the p sub z with 1 electron, and then you go back and you double up. I think of this, the analogy that I use to remember this one, is room sharing rule. Okay, so in your family, if you have lots of siblings, everybody wants their own room. So if the room is available, that's what we do. We each go 1 to a room. If there's not a room available, you stay in a room with as few siblings as possible. Like, you don't want lots of roommates. You want as few roommates as you can possibly have. The occupancy in these rooms is maximum of 2. So that's Hund's rule, according to trying to put siblings into their rooms. And finally, we have the Pauli exclusion principle, which says no 2 electrons can have exactly the same quantum numbers. In other words, no 2 electrons can occupy the same space at the same time. You cannot have 2 electrons with the exact same solution of the Schrödinger equation for atomic orbitals. We'll get into how to fill the orbitals again on Friday. We just talked about what the rules are here. We're going to apply the rules. To summarize, atomic orbitals are solutions for the Schrödinger equation and are probability functions. The relative size of the orbital is given by the principal quantum number n, an integer, and all electrons with the number are in the nth shell. The shape of an orbital is given by the angular momentum quantum number, designated by a cursive look in L, which corresponds to the SPDF designations for the shapes. These are called subshells. And the orientation of the orbitals in space is the magnetic quantum number, m sub L, and the off-bow principle says that we should fill lower energies first. Hund's rule says that we should fill degenerate orbitals 1 electron at a time before doubling up. And the Pauli exclusion principle says no 2 electrons can have exactly the same quantum number.